So my name's James Weaver. This is Johan Voss, and we're going to talk to you about something completely different, quantum computing. Going to go through the introductions really quickly so we can get to the meat of the presentation. I'm a developer and speaker for Pivotal, written several books mostly on Java. Pivotal, our mission is to transform how the world builds software. We're the stewards of Spring. We also have Pivotal Cloud Foundry. It's an app. It's a cloud platform, runs on top of AWS, GCP, Azure, on-prem, whatever. And then we also have a new kid on the block is production-grade Kubernetes. And we also have here in London and all over the world Pivotal Labs, in which we engage our customer with agile practices and developing and helping them do things. Love our technologies, but the coolest thing about working for Pivotal, the thing I like most, is our principles and practices, particularly that one on the right, be kind. You don't really have to tell me to be kind. I feel like I'm a pretty kind person, but it's really nice and refreshing to work for a company who, one of their prime directives is to be kind. And God knows we need to be kind to each other and treat each other like we want to be treated. And this bloke is Dr. Johan Voss, and he's the smart one. I brought him because he's the only PhD physicist on the stage right now, and so as I say things, he's going to keep me honest.
So, and Jim is the only kind person on the stage at the moment.
Okay.
But that may change during the presentation. So, I'm working with Java since its inception, worked with porting Java to Linux. At this moment, I'm mainly working for Gluon, where we try to, where we bring Java to mobile devices, so that you, as Java developers, can create Java apps and they run out of the box on Android and iOS. And you can connect them to the cloud with a Gluon Cloud Link. And that allows you to use your Java skills to create mobile apps, connect them to the cloud. You can create AI applications, for example, run them partly on a mobile device and on a cloud. And in the future, we intend to, well, you never know that you might run quantum applications on mobile or embedded devices. But so we're working on Java everywhere. Did you want to take that
great.
selfie?
Okay, so I forgot to tell you. I mean, Pivotal's a great company to work for. We'll go this way.
At this moment, I'm the only person on stage.
Yeah, let's go.
Okay.
So a great company to work for, but my boss has trust issues, and so he sends me all over the world to speak, but if I don't get a selfie with the audience, I don't get paid. And if you could really help me out, if he knows that you're all having a good time, then maybe I'll get a little bonus. I'm kidding, of course, but what I'd like to do is get a selfie with you if I could, and maybe get a crazy pose from you. So I'm going to go ahead and count to 3. Let's go over here. You've done selfies before, right? Okay, and so 1, 2, 3, crazy pose. Thank you. I'm tweeting this, so if you're not supposed to be here right now, you can start making up an excuse for why you were here.
By the way, who did see the presentation from Matthew Rand's first thing in the morning about AI? Yeah, where you saw that it's very easy to mimic celebrities, and so far for the value of a selfie with everyone in the room. It can all be made up, of course.
Where's your browser?
Yeah. Oh, are you really gonna tweet it?
Yeah, we need the browser because I need to show where the presentation is.
Yeah.
And all that. Okay.
Can you do it later?
Okay. All right.
I can go to the
yeah,
browser.
because we need to be able to show some resources and stuff. Okay, there you go.
Yeah.
Good. Okay, so this is where the slides are, by the way. There's lots of links in the slides, good resources, and so if you just follow me on Twitter, then right here is where the links to the slide are as well. Let's see. We also ought to see how crazy of a pose you guys did. Oh, nice bunch. Thank you. Thank you for cooperating there. I'm sure I'll get a nice bonus for that one. So what we're going to talk about, first of all, is we're going to introduce quantum computing to you.
You want to go to full screen again?
Okay.
You know how to do it?
Yeah.
Okay.
I have a colleague named Mark Heckler, And he does heckle me, but you're not him. Okay?
Oh, I'm kind.
Oh, yes. Okay. So with quantum computing, it's like history is repeating itself. I don't think anybody was here in the 1940s. I certainly wasn't. But back in the 1940s, everything was brand new with computing. Computers took entire rooms, and there were a limited number of bits. I remember stories from older colleagues that talked about how they would take these ferrite cores and weave iron thread through them and make, each one of those was a bit, right? And so software was at its infancy. So the picture on the left is a ENIAC computer circa 1947. The picture on the right is an IBM research quantum computer that takes a whole big room. There's a limited number of qubits, which we'll talk about, and the software is in its infancy. And so what we're going to talk about partially is why quantum computers. So quantum computers, if you look at the bottom there, we'll explain why here in a second, but quantum computers make direct use of quantum mechanical phenomena, which is really how the universe works, such as superposition and entanglement to perform operations on data. So instead of this artificial binary on and off kind of thing, as its underlying infrastructure, it uses the way that the universe really works to operate on data.
And that is often hard to explain because people are so used with the false image we have of the universe being everything in bits, zeros and ones, and that is not how nature works. But it's difficult for us because we are taught with this 0 1s, and now we have to think again in how nature really works, and that's right. Not easy.
That's right. Yeah, we went from analog, and then the cool thing was digital, right? 80s digital audio discs and things like that. But really, to really leverage nature, you have to go quantum. So over on the left is a quantum computer that they're building at Delft University of Technology, and I think you went to school there, right?
I did a PhD there, but that was not at quantum computing.
Okay. And then over on the right, actually, Professor Winfried Hessinger, he spoke here last year on the quantum computer that they're building. It's a trapped ion quantum computer, which Johan can talk about. And they're building that at the University of Sussex here in the UK. Yeah, I know I mispronounced Sussex. Okay. So why use a quantum computer? So there are some solutions to problems, and some of those solutions are feasible on classical computers. That's the ones we use nowadays. And some are feasible on quantum computers, and there's an intersection between the two. But there are some problems that will never be feasible on classical computers. And that's kind of the area that we want to explore, and the reason for being one of the reasons for quantum computers. And so those kinds of problems are characterized by taking exponentially long times to perform. You might call them NP complete kind of problems if you're talking about complexity theory. And so, but there is a middle ground, and so that's that right circle is what we're targeting today. And one of the driving factors is that transistors, that we see in computers, can't get much smaller. There's something called quantum tunneling, and because I have the luxury of having Dr. Voss here, he's going to talk about that struggle.
It's always easy to pretend that you're kind, and then for the difficult things, you blame your co-presenter. So quantum tunneling, yes, so transistors get smaller and smaller, but at a given moment, if you make them even smaller, then the quantum effects will come into the picture. At this moment, transistors are still big enough so that the quantum effects are not visible or are not influencing the classic circuits. But if you make them smaller, a transistor typically either or either.
Either one. Either
okay.
one.
Okay, both.
Yeah.
A transistor can keep current on the left and block it from going to the right, or it can open its gate and then it can go to the right. But in quantum mechanics, even if there's a gate, a quantum element may transfer through the gate, or it may suddenly be at the opposite side of the gate if the gate is small enough. So far for transistor logic in the world of the very small. So Moore's law will not forever lead to increasing resources because there's a physical limitation on the size of transistors. So if we want to get faster and faster computers, classic computers won't solve it in the future anymore. So we need a different concept.
Nice. Thank you.
Is it clear so far? Because do we want them to...
Yes, as you have questions, go ahead and ask questions, raise your hand, and I'll repeat the questions for the microphone. But yes, a question back there. And please shout it out. Okay, so how far are we to having like real quantum computers and to where it's solving real problems, things like that? Oh, how far are we from the quantum tunneling limit? That one? Quantum tunneling? Yeah, how far are we from that quantum tunneling?
How far are we from quantum tunneling? I don't know what's in laboratories. They are beyond. So they created transistors that are smaller than the ones that we use in our computer, and they don't work anymore. So that's, the limit has been achieved, but that does not mean that, that the limit of CPUs, microprocessors, and everything has been achieved, because we're making a big simplification. The computer does not scale only by the size of the transistors. There are other things, of course, but we're getting closer to the limit where laboratories. Do you have another word for that?
I don't know. I call it laboratories.
For example,
here they might call it laboratories.
The labs, for example, cannot go much smaller anymore.
Okay, thank you. So some of the driving factors are that smart guys like smart people like Peter Shor, back in 1994, came up with this algorithm for this quantum algorithm that leverages quantum mechanics, and he calls it, oddly enough, Shor's algorithm. And the idea is that one of the ideas is that with RSA encryption, the challenge, the reason why it's pretty secure, is you take this maybe 400-digit number that you created by multiplying two prime numbers, and it's easy to multiply two prime numbers, but it's really, really hard to factor that 400-digit number into two primes. And so that's, the inconvenience and the length of time that it takes is why RSA encryption is safe for the moment. And using classical computing, it could take hundreds of years to factor really large numbers. So what Dr. Shor did is he found a way to use quantum algorithms to do one of the steps that it takes to factor large numbers. And Dr. Voss is going to be talking about that in a little bit. There is a nice paper here. It's a very approachable paper at the bottom that Dr. Shor wrote in 1997 that you can learn more about that. So that's one. That's Shor's algorithm. Another one is Grover's algorithm. And that's an algorithm that he created in, I think, the next year, 1995 probably. And what it does is it does searching in unsorted data. So it's easy to find something in sorted data, but you have millions of records of unsorted data, then it becomes pretty hard to find something. It's like a needle in a haystack. So he created an algorithm that makes that much faster, that leverages quantum circuits. I like his quote here. He says, "Programming a quantum computer is particularly interesting since there are multiple things happening in the hardware simultaneously. So one needs to think both like a theoretical physicist for the quantum mechanical aspects and a computer scientist for the computer science aspects." And then here's Dr. Richard Feynman. Who has heard of Dr. Richard Feynman? Okay. Who watches Big Bang Theory, by the way? Okay, so Sheldon, when he plays the bongo drums over there on the right, he's actually giving an homage to Dr. Feynman, who, to relax, liked to play the bongo drums. And so that's, you know, Sheldon, being a theoretical physicist, was paying homage. And he had this quote. Dr. Feynman was one of the, you know, as far as quantum mechanics and quantum computing, was one of the visionaries and one of the pioneers in that area. I'm looking at Dr. Voss to keep me honest. And so he's got a great quote. He says, "Nature isn't classical, and if you want to make a simulation of nature," so you want to use a computer to solve real-world problems by maybe simulating chemical processes or other things that, you know, that are in nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. It's a great challenge. And so he's basically saying, you know, if you've got real-world problems where you're trying to simulate nature, and there are some real-world problems, by the way, you know, production of energy and you know, production of fertilizer, for example. One of the biggest uses of energy right now is creating, you know, enough fertilizer. And so if we could model those chemical reactions well enough, we could save lots of energy, and do more food production. And so, you know, there are some real-world problems that we can solve. So, like, speaking of chemistry, then, you know, because we're not all chemists, you know, computer scientists, you know, you don't have to be a chemist. But there are some libraries emerging, like Open Fermion, to where it abstracts actually a lot of the quantum computing part and a lot of the chemical part to where you can create applications using this API that begin to simulate nature, simulate chemical reactions, and begin to help us all solve real-world problems. Anything you want to say about that?
Yeah, I was thinking, did you want me to say something on the previous slide?
Sure. Go for it.
What do I have to say?
You can say anything you want.
Anything. So, adding to this, we currently try to solve chemical problems of nature, and so by doing some simulations, we try to simulate the structure of molecules, and that's the basis for many health research, and so. But it's extremely difficult because simulating a simple hydrogen module is already taking lots of memory and lots of CPU power. So complex structures, like human being, are extremely hard, impossible to simulate using classical computing. And one of the reasons that it is so hard is because we have to simulate for the quantum effects that are taking place at the very lowest level. And that is a bit silly, so we first create a model that's artificial, and then we use that model to explain what happened before. So the easier thing is that why don't we use the quantum principles at the very first place to start simulating and modeling. So, and that explains actually is the title of the talk Hacking Nature's Computer or Correct. So, because yes. We're using nature itself for understanding nature better. At this moment it's still abstract, so we'll become more concrete now about what is setting quantum computing different from classical computing, but we first want to set the stage a bit, right?
Yes, thank you.
Yeah?
Thank you very much. So another area that's very useful for quantum computing is something called quantum key distribution and quantum cryptography. So in China, they did an experiment where they took a ground station and they shot a photon. Actually, they entangled, if you've heard of entanglement, and we'll talk about entanglement, but they entangled two photons. They shot one of them up to a satellite, and then they did the experiment observing the orientation of the polarization of the photon in the satellite and at the ground station. And just like Schrödinger's cat, which we'll talk about, when you observe one, the other is observed in the same state. And so they did that from ground to satellite, and then they repeated the experiment. Well, a different team actually did it from satellite to ground, and they added to that experiment this thing called quantum key distribution. If you go back to the Shor's algorithm, how it's going to break RSA encryption someday, we need some better way. So what they're looking at now is using quantum cryptography, and as a first step, maybe using classical cryptography but then sending the key over quantum channels. And because of the nature of quantum communication, if you hijack or if you observe something while it's being sent from point A to point B, it collapses and no longer is valid. So you can tell, the receiver can tell whether it's been observed or not. And so they did an experiment in that area.
So here we already touched one of the key aspects of quantum computing. If I have 2 bits and I give one with Jim and I walk away with the other one, and I look at my bit, it says 0 or 1, then that doesn't say anything about Jim's bit. But in a qubit, and we will explain immediately what a qubit is, which it's the primary concept of quantum computing, they can be in an entangled state. As a consequence, if I have 2 qubits that are entangled, you don't say that, but Jim walks that way and I walk that way with my qubit, we don't know whether there's 0 or 1, but the moment that I look and it is 0, then I know that if Jim looks, it will be 0 as well. But before that I look into it, it can still be, for Jim, it can be both ways. So that is, qubits are connected, but not at the moment where you create them, but only at the moment that you measure them. It's not that I give him a 1 bit and I walk away with a 1 bit as well. No, they are in an undefined state, but only if you measure them, they become defined. But they become defined at the same moment. And that's something that Einstein and others didn't believe initially, because that actually means that the information, the moment that I read my qubit and Jim's qubit, and he may be only 50 meters away, but the Chinese did that with sending it to a satellite and back. The moment that you read one, that the others has a value as well, it seems to indicate that you can send the information faster than the speed of light. And that is something that Einstein and others had a problem with.
Okay, so then another area is machine learning. Part of, there are several challenges in machine learning. One is as a network is learning, what you're trying to do is take the cost out of the network, the artificial neural network, to where the inputs and the outputs, match the data and the computed outputs and the real data match. And so you do that by classically you do that with gradient descent, to where you're changing the numbers in the network and then finding a minimum. And there are algorithms, there are quantum computing algorithms now that are, as discussed by, for example, Carrie at a quantum computing meetup, that do that kind of thing as well. And there are just other ways, other really nice intersections between quantum computing and machine learning. So what I'm going to do is take you to the very kind of the basics. To really understand quantum computing, you have to understand quantum mechanics. And I'm not a physicist,
but you're kind.
But I'm a client. That's right. But I can explain it, and I can explain it to you in the context of cats, grumpy cat. And so we're going to go through the 3 axioms of quantum mechanics using grumpy cat. So Schrödinger liked cats as much as I like humans. By the way, and so there's a kind of an artist rendition of grumpy cat. That funny symbol there is called Ket notation. It was created by Paul Dirac, Dr. Paul Dirac, just a brilliant physicist back, several years ago. And it's just an easy way for physicists to manipulate vectors and to think about vectors. Vectors are, in Java or any other programming language, you can think of those as one-dimensional arrays. And so that is grumpy cat. So I have this microscopic cat. It's so small you can only see the cat in a microscope. And sometimes my cat is actually happy, and sometimes my cat is actually grumpy, but I've never observed him in between those states. I've only seen my cat grumpy or seen him happy. And so that leads to the first axiom of quantum computing, And that's called the superposition principle. The axiom is that quantum particle cats, I'm sorry, I'm not talking about quantum, I'm talking about my quantum cats, can be in any combination of grumpy and happy. So if you look at the top of that circle, in that state, my cat is happy. On the right, cat's fully grumpy. But if I go 45 degrees there, my cat is in a superposition, an equal superposition of grumpy and happy. As well as, if you go to 45 degrees down, right here, my cat is in an equal superposition of grumpy and happy. As a matter of fact, there's a link on this page that has kind of a simulation here that shows that my cat can be in an infinite number of states of superpositions, or if you think in terms of linear algebra, linear combinations of grumpy and happy as we rotate around this circle. And so these numbers that we see here are amplitudes. But basically, they are this particular one here. This number is half of is the square root of 1/2. So this amplitude from here to here, where the dotted line is, the dashed line, is that distance. It's an amplitude on the x-axis, and then the distance on the y-axis, and those are these numbers, half of or square root of half on each axis. So that's the superposition principle. Any questions on the superposition principle as it relates to cats? Okay. Then we have...
Full screen.
Yeah, I think I'm just going to do this.
Okay.
Right. Okay. So we can represent quantum states geometrically, like we saw with the circle. And we see grumpy and happy. And we can also represent them as a vector. So geometrically over on the left, but notice the grumpy state, which is here. The grumpy state, we can represent it with a vector of, one-dimensional array of two numbers. And the two values in that vector are 1 for the grumpy state and 0 for happy state. So here, that vector representation means that my cat is fully grumpy. That's this state. This state is the same as this state. So then the next one, the happy state here, would be 0 in the grumpy dimension and 1 in the happy dimension. And then some superposition of the two. Here we've got this point right here, which would be the root of 1/3 in the grumpy dimension, and then the root of 2/3 in the happy dimension. And so we could represent that with ket notation as well as with vector notation. So any questions on that? It's kind of a fundamental thing that we don't want to trip up on as we continue. Okay? Great. Thank you. So that was axiom 1. Cats can be in superpositions. Axiom 2 is something called unitary evolution. So my cat can change state over time. And here we have a grumpy cat, but then if we send my cat through an X gate, also called a NOT gate or a bit flip gate, then my cat will be in a quantum state of completely happy. Now, these gates can be modeled as matrices. And matrices are a linear algebra kind of concept where you can take a matrix here. This is a 2 by 2 matrix. And that represents the gate. That's how, it's actually kind of cool that you can take a quantum gate and you can very simply represent it with a matrix and actually do the math to simulate what's happening in nature with quantum mechanics. So here, this gate is represented here. And then we have the grumpy cat. Remember, the grumpy cat was represented by 1, 0. So here we have the grumpy cat. And then if you do the multiplication of the gate, the matrix, by the vector that represents the grumpy cat, then we end up with the vector that represents the happy cat, the 0 and 1. And there's a trick to vector multiplication when you're talking about these kinds of vectors with permutations, with 1s and 0s. Here we have a 1 and a 0, so the top dimension of the vector is a 1. And so we just pick out the first column of this matrix that we're multiplying it by, and that's what we bring over here. So that's the matrix that then flipped, that transformed, that evolved the grumpy cat in its grumpy state, in its grumpy quantum state, to a happy cat in its happy quantum state. Questions? Yes?
We gotta go fast.
Just going back to the previous diagram, we've got the kind of two states, grumpy and happy, which are at 90 degrees to each other. So if, at the bottom of the circle, you have essentially sort of negative happy.
Okay, so the question is, here we've got the 360 degrees, and so here we have kind of positive grumpy, positive happy, but then we have, like here, negative grumpy and negative happy. Well, the amplitudes are negative. It's kind of weird to think about, right? But the amplitudes are negative on the x and y, the grumpy and happy axes. And you'll see in a minute why that's okay.
It's just one way of representing.
Or Johan's going to tell you now why it's okay.
Yeah, well, typically qubits, so not cats, are represented in a block sphere, in a sphere, where the top is 1 and the bottom is 0. And then everything between is a superposition of 1 and 0. And that makes more sense than on a two-dimensional circle with... that is actually just to show the probabilities if you measure. But if you think about states 0 and states 1, then what's typically used in quantum computing is a block sphere, and we will show that in half a minute.
Yes, right, okay. And so, so one of the gates for unitary evolution is a Hadamard gate. And it's great for putting cats in equal superpositions. We can run grumpy cat through a Hadamard gate and ends up in an equal superposition of grumpy and happy. A Hadamard gate, and don't have to go through the math here, but is just square root of half, and with the negative square root of half here, multiply, that's the gate, and then we multiply it by grumpy cat, and then we end up with a superposition. And so the Hadamard gate is key for a lot of the quantum computing algorithms. And then axiom 3 is measurement. And so as Johan just did a spoiler alert on, the probability of measuring at a particular state is the amplitude squared. So if we have if my cats are in a superposition of root of 1/3 grumpy and root of 2/3 happy, when observed, there's a third probability, because that's the square of 1/3, of being grumpy, and 2/3 probability of being happy. And so then we can have multiple cats. I'm speeding up a little bit because I want to let Johan talk.
The principles remain the same, it's just more mathematics involved.
Yeah, more mathematics. And then here we could have multiple cats. So here we have 2 cats, they're both grumpy. So that's a composite state over there, which is composed of 2 grumpy cats, which is composed of 2 vectors, which represented by 2 vectors, and then you do what's called a Kronecker product on that, or tensor multiplication on that, where we multiply these two vectors, and we end up with then a four-dimensional vector, and the 1 there is beside grumpy grumpy. So this can be represented by this vector. And then the same thing with grumpy happy. Multiplying them together, grumpy and happy, we end up with this vector, where the 1 is beside the grumpy happy element. And then we could have 3 cats or 100 cats or whatever. So putting all this together, superpositions, that's axiom 1, evolution axiom 2, measurement axiom 3. Putting those 3 together, let's say we have cats in the state of grumpy grumpy. They go through a quantum gate, and then they're in this superposition. And then we put them through another quantum gate, let's say, and then they're this superposition. And then we take a measurement with half probability, then it's going to be in grumpy happy. With 1/6 probability will be in happy grumpy, and 1/3 probability will be happy happy, joy joy. So anyway, now we have quantum entanglement, and that's the last thing I'll say. We have 2 cats, Alice and Bob, and this is a quantum circuit in which we're entangling Alice and Bob. We're going to run Alice through a Hadamard gate, and as we saw, Hadamard gates are great for putting cats into superpositions. And so now Alice has been through the Hadamard gate, so our quantum state now is root of half grumpy grumpy, root of half grumpy happy. And then we run through a C-NOT gate, which is a controlled NOT gate. This is the bit flip down here. This is the NOT gate that we showed you before. But it only flips if this is on. And so that puts our cats into a bell state. I just put a little cat bell there. But the bell state is here, where we have equal superpositions of grumpy grumpy, happy happy. So then, if Alice got in the spaceship and flew to Venus, and Bob got in the spaceship and flew to Mars, in that position, once they've been entangled, if we observed Alice and she was happy, then when we observe Bob, there's a 100% probability that he would be happy. The other way around, if we observe Bob, for example, and he was grumpy, then Alice would be grumpy.
So that is actually what we were saying before. If you go back one, because yeah, that's good. Okay. If we have 2 entangled cats or 2 entangled qubits, and you send them through some gates, and then you move one away from each other, if you measure one, then you know the other as well. And that is something that you cannot do with classical bits.
Yes, thank you. And so, obviously, you don't make quantum computers out of cats. I suppose you could, but that wouldn't be good. So hardware representations of qubits, which Johan's talked about, these qubits, what can you make them out of? What can you represent a qubit with? Cats, I suppose. Go ahead.
Yeah, I think there are different hardware representations of qubits, but I don't think we have to go into details because
take it away, Johan.
running out. So qubits is something that we mentioned a number of times already, but what is it actually? So, and I think the picture of the cats is hopefully something that makes it more clear. So a cat can be grumpy or, what's the other? Happy? Happy or grumpy. But in quantum theory, it can be happy and grumpy at the same moment, and it's only when you measure it that it will fall back to one state. If you translate that to quantum mechanics, instead of a cat, we can have a photon, an electron or so, and they have spins, polarizations, and these are physical phenomena that can be in different states at the same moment, just like the cat can be happy and grumpy at the same moment. This is to answer the question from a while ago. This is how it's typically represented in what's called the Bloch sphere. You can have a qubit that's in the upper state or the state 0 or state 1, or on any superposition of those states. That is what we call a qubit. A typical bit is 0 or 1, and a qubit can be 0, 1, or a linear combination. In order to bring a qubit into such a linear combination, you have to apply, some physical process. There was that video of...
Yeah.
Okay, yeah, there, yeah. You have to apply, for example, you can send a very low energy pulse to a qubit, and that will bring it in a superposition state. And that is where the fun begins, because otherwise the typical gates that we know from classic computing, they are the same in quantum computing. But the fact that we can bring a qubit in a superposition so that it can be 0 and 1 at the same moment, that is unique to quantum computing, and that allows for fun things. So in the next minutes, I want to quickly touch how this can apply to software developers. Because at this moment, there's a big gap between quantum development and software development. And in the future, and it can be 5 years, 6 years, 10 years, or sooner, these two areas will have to converge. And we have to be prepared for this. So what are the consequences for us developers? So if we compare classical computing, there we have classic algorithms, and they apply to classic gates with transistors and so. In quantum computing, we have quantum algorithms, and they are applied to quantum gates. And one of the fundamental differences between the quantum gates and the classic gates is that operations on a single qubit may also affect the other qubits if they are in an entangled state. How do we get in an entangled state? Remember from the cats, if I still have that picture. Yeah, you can get to an entangled state by applying two gates, first a Hadamard gate and then a CNOT gate. So these are typical quantum gates. We don't have them in classic things. But if you bring some qubits in this specific state, they are entangled. So even without you having to apply more the same gates to all those bits, they will automatically be corresponding to changes in behavior of the root bit. In many cases, quantum software development is best done by splitting a problem into a classical problem and a quantum problem. Because quantum algorithms can be very good for certain problems and very bad for other problems. And a great example is Shor's algorithm. Who heard about Shor's algorithm before Jim started to spoil it? Okay, so that actually, who understood Shor's algorithm after Jim talked about it? Okay, so there were two people who understood what you were saying.
Sorry, I didn't do a very good job.
That's better than the previous presentation.
I'm really sorry. Yes.
But there was no one in that presentation.
Yes,
so.
right, yeah.
Shor's algorithm, you probably heard, if you heard something about quantum computing, what people typically hear is that it will break all the encryption because it will be able to decompose factorize keys. Now, that is not entirely true because Shor's algorithm will only fix a very small part of the problem. So this is the algorithm, so it's very easy. You can probably implement it now. Okay, done. So what did you do? You do some classical steps. So the first step is a classic algorithm. The second step, finding the period of a function, is also something that you can do in a classic way, but it will take extremely long if you do that in a classic way. And that is an algorithm that a quantum computer can do much, much faster.
That video, by the way, it's an excellent video to watch to learn about Shor's algorithm, the one that's in that link.
Yeah, and the slides are online, so you can watch them. So actually, I won't have time to go over how we work with gates, but it is actually the same as you work with the cats. So there are a number of software simulation tools that allow you to do this. And actually, so replace the grumpy with 0 and the happy with 1, and then you can do the same as Jim showed before, but then in quantum simulation things. One, for the Java developers, I often got a question, so why is it that a quantum computer can be much faster? Because if you have the same amount of qubits than the amount of bits that you had before, a quantum computer can put all those bits in entangled states and do many things with them at the same moment, but in the end, you will still only measure the same amount of bits that you started with. But think about it as in Java, you can have parallel processing. So you have a stream that's then decomposed, and parallel processing happens on every element, and in the end, the result is then sent back. And that allows you to do much more processing at the same time. And the quantum computer gives us for free this parallel processor. So there are many tools around that can help you with quantum computing. One of the important areas of research is at this moment quantum computing simulators, because there are no quantum computers yet that are able to break encryption, at least not with enough bits. But one of the most challenging parts is finding those quantum algorithms, because Shor's algorithm for finding the periodicity of a function involves Fourier transforms, which are easily done in quantum computing. But man, you have to think about that. So I still wonder how he came up with that idea. If you have to sort a list, that's easy. I mean, everyone learned that at school, how to balance a tree, and so that's easy. But quantum algorithms require a different way of thinking. And therefore, people need simulators to check if their ideas are good. So there are a number of quantum simulators that are excellent in a way that they mimic quantum, real quantum behavior. But they have a big drawback, and that is that you need increasing amounts of memory if you want to simulate increasing amounts of qubits. Yeah, otherwise, we didn't need a quantum computer if we could do everything with a simulator. So we're at the Java conference. So we started the Java-based quantum renderer and a quantum simulator. And if you look at those links, those are GitHub projects where we allow to render, create circuits, and use them to render the quantum effect. So I will very briefly show a few things of this. One of the things that if I can go to NetBeans. Yeah, here it is.
You have to make that font bigger.
Yeah, but I have to restart it.
Okay. Or do you want me to just make that bigger for you?
No.
Okay.
I have to quit NetBeans. So what you see here, while I'll restart NetBeans, you see here a quantum program. Oops, there we already go. Can you force quit? Or is it already gone? How can you force quit on Apple here? Okay, force quit. Okay. So I don't want to show the specific code there, but you might see that there we create a program, and a program is a quantum program. We add a step, and in that step we add a gate, for example, an identity gate, and then we add that gate to that step, and we run the program. So you can also run this on the cloud. For example, we run it on the Oracle Cloud. We have a cloud simulator running there. And I can start that cloud service. So what we now have is a quantum computer simulator running on the Oracle Cloud. And our quantum computing library is going to connect to that cloud. So if I click on execute test file, then what you will see is that the computing requests are sent to the cloud. And that is because it is it takes way too much memory to do locally. We call to Glue on Cloud Link, which is our bridge between local processing and the cloud. And there you see that we sent this request to the cloud. We want 2 qubits with one with an X gate. And this is the result that we get back. So this is the result, qubits with some of the probabilities. If you see, this is what the cloud processed. So it has tons of debug information, and it sent the result back to our NetBeans, and it says test test passed. So there's one thing that you can do with this cloud simulator and with Strange in general. I'm going way too fast over this, so I hope that you will just look at it later when you have time. But one of the other things, and I think that's a cool thing, is this is also part of StrangeFX, and it allows you to visualize what happens to a qubit when it encounters an X gate. Did you see it changes? We'll do the same with the bottom qubit. It is in the down position, and now it's changing the up position because it encountered an X gate. This is code that we use for it, but if you don't like to write code, you can also do it, and now I really have to increase the font size, but I have no time probably. You can also, we have a JShell application. Who is using JShell here? Okay, this is the Java REPL. So if you're using Python, if you're used to Python, you want to create applications by just, well, typing single commands. Is it a little bit readable in the back there? Or do I have to? I'll quickly create a qubit here. So I create a qubit 3D, and then I call qubit.show. So this is all Java code, and here's a qubit that I have. So it's 3D rendered using JavaFX and fxyz. Then I can ask, for example, qubit.flip, and you will then see that the spin of that qubit changed. So this is a Java library that might make it easier for you to understand what happens with quantum computing. We're out of time, so I don't want to hold you from lunch, but if there are questions, we're happy to answer them, of course.
Well, thank you very much for your attention.